All right, let's get started. My name is Greg Badesky, and I'm going to be walking you through the nuts and bolts of what we're going to see today during our Rubin Virtual Data Academy. Thank you very much for joining again. I'm gratified to see that there's about 30 people who are our attendees, which is really quite wonderful. So this Virtual Data Academy is basically something that we've done in the past called the Virtual Summer School. And it's basically the goal of it is to get people familiar with the analysis and reduction of the Rubin Observatory data. Today is day one, and because of the fact that we're starting, most of you, if not all of you, have not been on the previous session in the morning California time, I'll just go through and just give you a full rundown of what to expect. The most important part is that Rubin Observatory will produce such a huge amount of data that you will essentially not be able to work on the data on your computer. You'll not be able to download the whole data set and just work on it. Instead, you'll be working what we call next to the data. So people who are participants in the Rubin, meaning people who have data rights, will be able to get an account on the Rubin Science platform and work there. And the reason for those previews that we're taking here is for you to become familiar with how to use it before the data starts flowing in. So we're, of course, going to be working on simulated data. There will be data that were simulated for cosmology purposes by Dark Energy Science Collaboration. That was about 300 square degrees on a sky of galaxies, stars, and so on and so forth, but no solar system objects. There are images and catalogs of those data sets. In addition to that, there was a separate simulation that was designed to basically simulate solar system objects that essentially move on the sky. And that is the data preview 0.3 set. And you will see both of them today. Doug Tucker will be presenting DP 0.2, and Jake Kurlander will be presenting DP 0.3 data. DP 0.3 is somewhat different than DP 0.2 because it does not contain any images. It's just catalogs of objects, and the catalogs are set up in such a way that there are individual, basically, images in those catalogs, not images, but I should say individual measurements of the source positions and intensities. All right, so let me just introduce you very briefly to the Rubin Science platform. So what I'm going to do now is I'm going to stop to just basically switch to my other screen. When you come into Rubin Science platform, which is data.lsst.cloud, you will actually see something that will look just like what you have in front of me. You need to, of course, to log in to be able to connect, and you can log on by using your identity, and you probably go through a little bit more complicated process, but this is basically what you're going to be seeing. And again, you will see quite a bit of the notebook platform, notebook instance of the platform, but link to this. Sure, I certainly will do. We'll put the link in the chat window, unless Jeff already did.
Yeah, I did put it in there.
You did. Thank you, Jeff. That's great. So this is the Rubin Science platform, and you'll come to this in a second. But I just wanted to tell you that there are two main instances: the portal aspect, which is basically user interface type thing, and then there's a notebook aspect that you will see soon from Douglas. So let me click on the portal aspect, and without going very deep into this, you probably will see some more of that tomorrow, and then on Thursday, you can go into either DP 0.2 catalogs, and there's a bunch of different tables within those catalogs. And you can go to DP 0.3 catalogs, and there also will be a bunch of tables in those catalogs. You will learn more about those tables because those tables are also accessible from the notebook aspect. Okay, so I'm going to go back to my previous screen, and we'll tell you a bit more about our team. So the organizing committee for the 2024 Rubin Data Academy consists of a number of people, and I think that I see that at least some of them are on this call. I'm Greg Badesky, and I will ask everybody else to maybe just say what institution they're associated with and what is their scientific background. Bulk of my work is in extragalactic astronomy. I'm interested in multi-messenger astrophysics. So not only do I work on optical data, but also on gamma ray and X-ray data. And I am Ed Slack. I'm a senior staff scientist here, and very much look forward to Rubin. So Jeff, I know you're on the line as well, so go ahead.
Yeah, hello everybody. I'm Jeff Carlin. I work for the Rubin project office. I have two roles, one in the data management team and then another in the community science team. And my science interests are focused on dwarf galaxies, especially dwarf galaxies that are satellites of larger galaxies or of the Milky Way, and just the Milky Way in general.
All right, thank you. I see Christina Williams is on the call as well. So Christina, go ahead.
Hi, I'm Christina Williams. I'm part of the Rubin community science team at Noir Lab in Tucson, Arizona. I've been a part of the team for a couple of years now, and my research interests are in massive galaxies at high redshift.
All right, thank you very much. And Douglas will be presenting in a bit, but go ahead, Douglas, and you can say a few words about what you're up to.
Hello, I'm Douglas Tucker. I'm at Fermilab, and I work with large surveys. I've been involved with the Sloan Digital Sky Survey, the Dark Energy Survey, and now Rubin. I've been involved with Rubin for about 5 years.
Wonderful. And I believe that Jake connected as well. So go ahead, Jake.
Hello, my name is Jake Kurlander. I'm a second-year PhD student at University of Washington, and I've was on the team that generated DP 0.3.
Right, so Jake is a bit of an insider here, so he will be able to tell you quite a bit more later on in this section today. Okay, so this is the organizing committee, and let me just go very quickly through some of the resources that we have. If you are at all interested in leaving a comment or asking questions, you have multiple ways to do this. You can either go to Slack channel and you can click on that link to sign in. And another possibility is, of course, the chat window in the Zoom, and we'll try to pay attention and make sure that we answer all of your questions. There's quite a bit of material that you can peruse on your own in the future. You might have seen some of that in the email messages that came from us earlier, but there's information on kickoff, and that's part of the delegate resources here. You can probably see this screen. And the important part is that you have the variety of virtual events, and DP0 kickoff sessions are here. There's 2 of them for DP 0.2 and DP 0.3. In addition to all that stuff, you have, of course, the Rubin Science Platform, which is where presumably you're connecting. And you can do this, you can actually participate in two different ways. You can either listen to our presentations and just take notes, or what's even preferred, instead of listening to the presentations, you can actually connect to the data.lsst.cloud and try to follow through via notebooks. And I will show you in a minute how to do the connection to the notebooks themselves. Okay, there's plenty of documentation and resources. And as I mentioned, the DP 0.2 and DP 0.3 simulations are distinct. So the documentation is somewhat different between the two. But all the notebooks reside in the GitHub repository, which is listed here, and you can pick them up from there. Not for today, it's not that important, but for future presentations, we also have presentations of tutorials via the portal aspect of the Rubin Science Platform, the one that I showed you earlier. And again, those are separate for DP 0.2 and DP 0.3 repositories for the portal tutorials on GitHub. So this is where you can find them. Okay, one thing that I should mention, or maybe I should stop here if there are any questions from anybody. Let me just take a quick look at chat window, but I suspect that this is only the material that Jeff has presented to everybody. Okay, so one thing that Melissa asked me to mention to you is that in addition to the community science team, which is basically part of the Rubin Observatory, we also have sort of an independent committee, it's advisory committee that is known as the Users Committee, which basically is a committee that is supposed to collect feedback from you about the Rubin data products, the science platform, the community science team, anything really that is related to Rubin, and the best way to really connect them is to either go to their website, which is listed here, and I think Jeff already posted the link to those slides. And they have 2 formal meetings a year, and one of them is usually during the Rubin community project community workshop, which happens in August every year. This year will be a little earlier in July. And again, there is an email address to contact. And since we're recording this session, even in the case if you happen to have missed it, you probably will be able to play the recording later on and get all the information. The members of the committee are listed here, and in fact, one of the members of the committee, Vincenzo Petreka, will actually be presenting in the academy. Unfortunately, Vincenzo is in Europe, or fortunately or unfortunately. So you probably, if you're only participating in the evening sessions, you will not be able to see him because at this point it's probably well into middle of his night. Other people are Igor Andrioni, Anuprita Moore, Dominique Bottigny in France, Vicky Sarajeni, Anya van den Linden, Alejandra Munoz Aranciba, Daryl Seligman, Matt Wiesner, Alessandra Corsi, Matthew Holman, who's actually the chair, and Michael Wood-Vasey. So those people, you might know them. If you reach out to them, if you have any questions or something, they're extremely responsive. And they've been really terrific in providing us a lot of really great information about what to do. Okay, so I'm trying to think what is it that I might be still missing, but I'm not going to be really doing much on the Rubin Science Platform portal aspect. It's going to be primarily on the notebook end. But one thing I should mention, the question that very often comes up in all this context is, should I be working primarily on the portal or should I be working on the notebook? And the answer of that is pretty straightforward. It turns out that the portal is extremely powerful. It's very flexible, but at the same time, it's relatively easy to use. It turns out that if I go into, again, my instance of the portal, I can tell you that there is just a huge amount of different tools that you can have. You can put constraints in spatial, temporal, and object ID searches. You can select different outputs, column selections, and you can also add additional constraints for those. So if you want to create, for instance, a list of all the stars that are within 1 degree of some field, it's pretty straightforward. If you want to have the list of those stars and list of their fluxes, and maybe even you can create a list of colors, something very similar to what you're going to be seeing in Douglas's presentation in just a few minutes. So let me stop here, and in the remaining 2 minutes before I hand over to Douglas, maybe we should open the floor for questions. So please either raise your hand or put the question in chat, or you can even put it into a Slack channel. Jeff, am I missing anything?
I don't think so. I haven't seen anything.
Okay, great, wonderful. So again, the agenda for today's session, we call it session B, is right here. And we're going to start with this overview of the Academy, which is hopefully what I gave you just now. I talked about portal versus notebook aspect, and most of the presentations with the from Jake and from Douglas will be primarily working with catalogs. We're not going to touch images. That's going to happen a bit later. The specific notebook that Douglas will be going through is Notebook 01 for DP 0.2, and he's going to be introducing the DP 0.2 and creating a color magnitude diagram for bright stars. And then afterwards, Jake Kurlander will go into the DP 0.3, and he will just give us a nice overview of DP 0.3, and then he will talk about ephemeris investigation for solar system objects. So for those of you who want to actually follow notebooks step by step, you probably will have to connect to notebook aspect of the terminal, and then you have to click code and copy the command, okay, that is here. And you have the link to the slides in your chat window. And then finally, you'll have to issue the notebook aspects terminal command line the following two commands. And then the fourth one will be where today's presentation actually will be. And this is the presentation by Jack Kurlander on TP 0.3. So let me stop here and allow you to maybe go into the, for individual attendees, go into the Rubin Science platform, and then if you wish to go into the notebook aspect. But of course, you can follow through if that's what you prefer to do. All right. I don't see any questions, but do feel free to ask questions, because for us it's really important. What are the things that we maybe are not exposing here properly? So questions are actually welcome, not only and encouraged. So feel free. And again, as I mentioned earlier, we are recording this, and we're going to post the recording on the most likely on the Slack channel, which is listed on the resources page. All right, I don't see any raised hands. No, nothing in the chat. So at this point, maybe I should stop sharing, and I should hand over to Douglas.
Okay, thanks, Greg. Let me share a screen here. And okay. All right. So for those who wish to follow along, I'll put this in the chat window. Oops, I lost my chat window. There it is. You may wish to go to this data.lsst.cloud, and that will bring you to this landing page for the Rubin Science Platform, or RSP, at the Interim Data Facility, or IDF. So here we see we have three different aspects that are shown from this landing page. The portal, which Greg mentioned briefly earlier, and in later sessions, not tonight, not during the B session today, but in future sessions, there'll be some tutorials on the portal. We'll discuss the notebooks, and there's also APIs, which include also, for those who are familiar with it, how to access Rubin data using, say, the TopCat graphical interface and virtual observatory graphical interface. And if there's interest, we could have a breakout session on TopCat during the breakout session later during this later on. But first of all, I mean, for those who haven't done this before, we'll log in. And if you have trouble logging in, there's people here, just send a note in the meeting chat or on Slack. There's people who can help. So I'm at Fermilab. I'll log in through my Fermilab credentials. Okay, so now I'm logged in. You see that I have my name is up, my username is up here, and I will connect into the notebook aspect. And this opens in the browser a container, like so. We have in the browser, we have a launcher window and a window showing basically the contents of my home directory on the Rubin Science platform, specifically on the IDF. I typically open up a terminal window at the beginning, and this opens up basically a Unix/Linux environment, and you can use Linux commands. Oh, I'm still logged in. Okay, okay. Usually you log in and you go to your home directory. Actually, let me make this a little bit bigger so people can see that better. And you can run Unix-y commands, Unix-like commands here. Over here is my directory. I apologize. My directory here is kind of a mess. what you will probably have are a data directory, a notebooks directory, and a work directory. For this particular, for right now, we are going to go to the notebooks directory. And into the tutorial notebooks directory. And what we want to do is we will go, here are various Python notebooks. We want this DP02_01 introduction to DP02.ipynb. And we'll double click on that. And we'll open a tab in this other window. And this is what our notebooks, these Jupyter notebooks look like. I know many of you have a lot of experience with Jupyter notebooks already, but not everyone does. So this is basically, it's just basically an introduction. We're just basically an introduction here, and we will also, in the end, create a colored magnitude diagram from objects from the COAD data from the DP0.2 data set. So, useful things to know is checking the pipeline. Oops, that kind of gets ahead of me. There is the pipelines version that you want to use. It's the weekly 2024_16, which when we, oh, I'm sorry, we didn't log into that. I will do a step back. And I will do that step back using a trick that can be useful in the future by, and I'll put this in the chat, going to this home directory, and I will, okay, I had this right before, so I had my server running. I should have shown you the step before, so I'll show you now how to. So here I'm stopping my server. I'm going to restart it. I'm going to launch the server. Usually first come to this page where you have the server options when you first log in, and there's a recommended version of the server, of the kernel to use, of the pipelines to use, and the size of the container that you're going, the server container that you're going to run. Generally, medium is fine, although you do want to look at and you'll click on start, and this will take a few seconds, and it'll bring us back to where we were. And in those, okay, so when we get back to where we were and into that notebook, that header will tell you what version of the pipelines you should use, and generally it's the most recent, the recommended version, so you don't need to worry about it. Sometimes you need to sometimes there's a couple places where you need to use a different version, and there's also and also sometimes you need a larger version. There's a couple of notebooks which use a lot of data, and you use the larger container size, server container size, not the medium size. But generally, the recommended and medium work fine. Let's see, we'll go back to tutorial notebooks and DP01 introduction. Okay. All right, so this is all up here. It says the weekly and container size, and okay, that's fine. So we will use, so we'll just kind of show some things about how to use a Jupyter notebook. We'll also use what's called a virtual observatory service called the TAP service to retrieve catalog data from the COAD catalog from the DP0.2 data set. We'll also use the Butler, that's something that's in-house creation, to retrieve and display an image of a deep COAD. We'll kind of skim over this. We don't have a whole lot of time, so I don't want to spend too much time on the introduction, but just some basic things. So this notebook demonstrates the basic functionality of the Rubin Science platform, or RSP, and we'll use the TAP service, and we'll use matplotlib to plot catalog data. We'll use the LSST Butler package to query and retrieve image data, and we'll use the LSST AFW display package to display images. Okay, this notebook uses the data preview 0.2 data set. This is the data set which uses a subset of the Dark Energy Science Collaboration's Data Challenge 2 or DC2 simulated images, and these have been reprocessed by Rubin Observatory using a relatively recent version of the pipelines. So this data set, this DC2, is 300 square degrees of simulated data in the LSST filters UGRIZY down to about the 6-year depths of so out to about year 6 of the survey, all simulated data, and it contains single epoch images, or basically single exposure images, exposures, and co-ed or stacked images too. Okay, for how to use a Jupyter notebook, or we are using one right here. So it's a Jupyter notebook is composed of a series of cells, and there's 3 types of cells. There's code, in this case Python code, which you can run. There's markdown language. That's what all this text is in that we've been looking at so far. And there's raw cells, and those are basically what you see is what you get. They don't run code. You can type code in there, but the raw does not run it. It is what you get, and you can when you're creating code, you can use this thing down here for markdown code or raw to determine what sort of cell you're creating. Here, very briefly, this is a code cell, and has some comments, and also does a simple hello world. And to run it, you hit Shift Enter or Shift Return, and you'll see the little thing here. It's changed. It says it's run. It says the first one is run. It gives you how long it took to run, about 3 milliseconds, and it gives you the output. There's also this. This is Markdown. If you do a shift return here, it doesn't do anything. But to look at the contents, you can double click the cell, and this is what the Markdown looks like. It has a comment, and which you don't see, and it's written in RST Markdown language. You can also use a certain amount of HTML in these Markdown cells, but these are basically for doing text. Okay, and here's a version of a raw cell. You see up here it says raw. It looks like a code cell, but if you do Shift Enter, it doesn't do anything. Most often you'll be using Markdown cells and code cells. Raw cells are not used so often, but they are there. Continuing on, Jupyter Notebook how-tos. Okay, let's not do this now, but you can, if you want to, execute all the cells one after the other. You just set the notebook to run all the cells one after the other. And to do this, you can go to this kernel menu item and go to restart kernel and run all cells. And that will just clear out any output that was already there and just rerun everything. Let's run everything to the end of the notebook. Another place you can do this is you can also hit this. This is the same, basically the same thing as this fast forward button here does the same thing. Another thing you is also useful to know is, say you're running something and one of the cells gets stuck and it's in like an infinite loop or something. You just want to stop if it's running too long. And to do this, you can once again go to this kernel and basically let's see what do we say here explicitly. You can restart the kernel and clear all outputs, and this will it may actually, if it's stuck in some weird loop, it may take a little while to stop, but it will stop. It may take tens of seconds, maybe up to a minute, but it will stop, and then it will clear out everything, and then you can try to rerun things. Okay, the kernel that here is the computational engine for the notebook, and the RSP uses Python 3, and it can be thought of as a live compiler. Restarting the kernel and clearing all outputs basically means that all the defined variables are removed from memory and all code cells revert to its unexecuted state. Let's see, other interesting things. Well, if you want to, so you may note that we have various headings here. We can view a table of contents of the notebook. If we come over here to this leftmost vertical menu bar and click on this thing that has a dot and three lines with a dot in front of each line, and that changes this into the table of contents. Now let's go back, let's switch it back to the original, which is click on the folder symbol up here, and it goes back to just showing the things in that particular folder. Another thing that might be useful is, say you start this up, but you forgot what version of the pipeline you're running. Simplest thing to do is go down to the bottom. Let's see, I'll just annotate this briefly. There it is. Okay. You can go down to the bottom, a small window of a small horizontal window at the bottom of the browser in this tab, and it'll tell you what version of the science pipelines you're using. In this case, the weekly 2024_16. It also shows you that you were using a medium-sized container. Okay, I'll clear that out. You can also run a couple of Unix commands from within here, and do basically the same thing. It tells you it's running weekly 2024 and various other details. Okay, any questions at this point? All right, let's continue on. So package imports, we will often some standard ones that you will often use will be NumPy, which is a scientific computing package in Python, Matplotlib, which is for plotting in Python, Pandas, which does wonderful things for to manipulate data, tabular data, in forms of Pandas data frames. AstroPy, which is a Python package of various useful astronomy tools, and various LSST packages, which are packages from the LSST science pipelines, and include, for instance, the LSST.RSP package, which enables image and catalog access via the TAP service, the LSST.daf.butler, which package which enables image and catalog access via the butler, and the LSST.geom package, which has helper functions for image metadata, and the LSST.afw.display package, which enables image display. And hopefully we'll have a chance to see all these. So here we'll just do a Shift Enter, and we will import all these things. You can run this other cell to see the version of these different packages that you're using. If you're interested in seeing aspects about the given package, you type the package name, then dot, and then hit dot, and then tab, and that shows you various functions and so on that are available through in that package. You can also, and we won't do this now, you can also do a help and the package name to get various help for that package. Okay, so moving along now, actually accessing some data. So we use a table access protocol, or TAP service. The protocols for TAP were devised by the International Virtual Observatory Alliance, and LSST Data Management has created a TAP service that follows the international the IVOA standards. TAP service uses a language similar to SQL, or Structural Query Language. It's called ADQL, for Astronomical Data Query Language. We note that not all ADQL functionality is currently supported by RSP for data preview 0, but as time goes by, more and more features become available. Okay, we will start this service. And here we're doing it for DP 0.2. If we want DP 0.3, there's use a slightly different value for that you pass to this command. And Jake will show us in the next tutorial. So we'll just get that. Okay. You can send queries, and if you want to look at tables, you can look at, there's different ways of looking at that, either an AstroPy table or a pandas data frame using a couple of functions we'll see a little bit further down. First, we'll just uncomment out this exercise 1, and we'll also do exercise 3 just very quickly. So ADQL query, here's a string. ADQL queries usually have 2 or 3 parts to them. A select for what columns you want, a from for which tables you want to access. And there's also often a where clause to restrict what you return. So he'll create this query, we'll send it to the search function, and then we'll convert it into a pandas data frame, and then we'll output the results by hitting Shift Return. And then you see the various tables that are available here. And later on we'll be looking at particularly at this one, this DP02 DC2 catalogs.object table. We'll skip exercise 2. Let's jump to exercise 3. So here we select a few columns from the column table in the TAP schema, and here we are only looking for columns in the DP02 DC2 catalogs object table, and then we don't print out the whole table because it's a long table. We'll print out the number of columns, and the number of columns is 991. That's a lot of columns. So we won't look at this. If you want to on your own, you can take a look. It's a lot. Okay, now let's jump over to 2.3. We'll retrieve actual data from TAP. We'll look at the object catalog. We note that the LSST query services, or QServe database is sharded by RA and DEC. So if you want to do fast queries, you might not want to search the whole catalog, but just small areas of RA and DEC. You can also retrieve a small sample of rows by saying the max record to a small number, or doing a select top. And we also select using detect is primary, because there's a deblending process that occurs, and everything is recorded, but you only want the final result. So you want which are given a primary flag of 1 or true. Okay. I'll skim over this. Okay. There's ways of, everything is in flux. It's nanojanskis, calibrated nanojanskis way, which generally you want to convert things into 80/90s. There's some description here. We will sort of skip over this, except looking at the use center coordinates. This 300 square degree area sky has a center that's roughly at 60 degrees RA and minus 37 degrees DEC. We'll actually jump over and grab 10,000 of these. So we select the top 10,000, we grab the RE and DEC, we grab the G, R, and I Calib flux, which is a 12 arc second radius aperture. Maybe it's a diameter. I don't remember. We'll grab the object catalog, And we'll use this where clause that will tell us that look at only things within 1 degree of that centered coordinate that we pass to it, the 67 minus 37. We only want detect is primary equals 1, and we want moderately bright things. So we want things brighter than 360 nanojancies in GRI. We are only looking at stars. So we want the extendedness parameter to be 0, not 1. And then we'll just print the result. We'll print the length of the result. Oh, I must have forgotten something here. Oh, yes, I need to define the user center coordinates. And I guess we could quickly do this, but we'll just ignore these other things. Okay. So we'll do the results table. And we have RA deck, the calibrated magnitude in GRI, and the error in G. And then we'll convert this table, this AstroPy table, into a pandas data frame. And then we'll skip over, we'll make a color magnitude diagram using matplotlib. We can use, so we'll use this plot command, and we'll do we'll make the G magnitude as the y-axis, and we'll have R minus I as the Z as the x-axis. We'll plot circles, so we'll have use the O to tell it to plot circles, the size, the marker size of 2, and the transparency as 20%, 0.2. And we just click on this, and we get a color magnitude diagram. Now, the red stars are quantized due to their colors are quantized due to the simulation. It's not that we won't see that in the real data. At least if we do, that'll be very interesting. But we should not see that in the real data. Let's see. Let's now quickly run over and look at image data. So typically you'll look at single images, which are calibrated exposures or CalX images in a single exposure, or you look at deep coads. Coads are tessellated. There's a sky map which breaks up the sky into tracts, and those tracts are further subdivided into patches. So to get a coad image, you want to know the tract and patch. Here we create an instance of the butler. So the butler is just a mechanism that allows you to query data, grab data, without necessarily knowing what the file type is or where it lies. So it kind of simplifies that matter, because things could always change over the 10 years of the survey and where things are located and file formats. So this kind of hides all that underneath. So we want to use the DP02 repository and the 2.2i/run/dp0.2 collection. And this defines the butler pointing to that collection of data. To identify and retrieve a deep coad, well, someone has previously identified a nifty, very nice looking galaxy cluster at RA 55.74 degrees, RA deck of minus 32.269. So, and we'll use what's called a sphere point to locate the tract and patch. So here we define the RA index, and we create a sphere point, which has that information. Then we read in the sky map, which tells you about the tessellation of the data DC2 data set. And we grab the sky map, and we use the sky map to find the tract and the patch for that RA index that's in that sphere point, and then we print those out. And we find out it's in tract 4431 and patch 17. And okay, we want that coad, and we'll just grab the I band. So so for a coad, you need to identify uniquely a coad, you need the filter band, in this case I band, the track number 4431 in this case, and the patch in this case 17, and you use the butler to get to that coad, that coadded data. And then finally we can display it and we use this using the AFW display. We'll set as the default backend matplotlib for plotting. So so AFW display uses the internal workings of matplotlib to do the plotting. And then we'll just go ahead and plot it. So using simple matplotlib commands. For those of you who have used like DS9 in the past, here we're basically just doing a inverse hyperbolic sine z and lookup table and a z scaling for the scale, and then we just go ahead and we plot that. Oh, I forgot. Sorry, I forgot to do this. I should have ran. I forgot to run the first cell. Okay, then we'll run this, and lo and behold, here is an interesting cluster of galaxies. And that is basically it. So we have some time for questions. Do we have any questions?
The only questions I've seen were regarding the recording, and I think we are recording this as we speak right now, and that will be posted in the recordings channel and eventually on the website.
There was one question about how long your server stays active, and I don't remember the exact answer. I just know that sometimes it'll be there for a few days and sometimes not. So I don't know if anyone else has a better answer.
Well, definitely once a week there's the patch Thursdays, which and at US Pacific time of about between 3 p.m. and 5 p.m. they basically reboot things, and basically all your stuff will get shot down then. So but I mean the changes that you made will stay in the will be preserved generally. Although it does help if you do remember to occasionally go over things that get automatically saved, but it doesn't hurt to occasionally do a save notebook or basically where's that actually just plain old save because I haven't made a change. Oh, there's read only, so I can't save that. Okay, yeah, if you want to make changes to things in the tutorial notebooks, you should copy them over somewhere, and then you can, yeah.
Yeah, I was just going to suggest that we should note that the tutorial notebooks folder is always read only. So if you want to experiment and make changes and be able to save those, then you'll want to copy it to a different folder, as Douglas said.
Oh yeah, yeah. All right. Why don't I stop screen? Stop. Oh. Someone asked about the butler. Okay. So yeah, sorry. I had to skim over the butler because I was running out of time. I thought I was running out of time. But it's basically a way to grab data without actually it's something that was created by the data management team, Rubin LSST's data management team, to be able to grab data, typically and mostly image data, although you can also do catalog data, but you don't need to know the details of how that data. The user does not have to know the details of how that data was stored, either the file format or where in a directory structure things are. It's basically set up so the user does not have to worry about that. That one just needs to say, for a deep coad, know what the tracked patch and filter band is to grab a given deep coad, or for a single epoch image, you need to know what's called a visit. Oh, cats! I forgot. I'm blanking out. Jeff, what do you need for a calyx? It's the
then you'll need that each detector is separate, so you need visit and detector.
Yes,
And
yes.
I think that's enough usually.
Yeah, yeah. There are other notebooks. I'm not sure we get to them in this school, but in this academy, but much more data, much more explanation about the Butler is in the DP 02_4A and 4B notebooks. So that's a useful resource too. But generally for catalog data, we tend to recommend using the TAP service. And for imaging data, the Butler. Although Christina Williams here has written a note, written a tutorial on what's called the OBS-TAP service, which is basically another way of accessing the images through a variation of the TAP service. Right.
There's one more question in
there's another one.
Slack that we could probably address quickly. The question is, could we quickly go over the pipeline versions and why you might want to change to a different version?
So generally you don't need to worry about that, but there are a couple notebooks which require, because the data were processed with a different with an earlier version of the pipeline. It's one of the notebooks. And Jeff, do you remember which one it was? Was that I think you wrote this
It's
one. It was
notebook
on
9. It's at the very top. There's a folder that custom
yes.
CoAD one.
So yes, this here is a notebook which you basically create your own. You decide, oh, I want to redo the CoAD for this area of the sky myself, but since some things have changed in the pipeline from when DP 0.2 was run and processed, you actually need to go back to a version of the pipeline that's compatible with rerunning this CoAD step. So there's one instance where you might want to use a different version of the science pipeline. But generally, you want to just stick with the recommended version. That's when you go to that landing page.
All right. I think that we don't have any more questions, so maybe we should consider switching over to Jake's presentation. But before we go there, I would like to mention to you that in the after Jake's presentation, we'll have some time set aside for you to either co-work in groups, or comparably, maybe you prefer to get a little bit more extended information about anything specific. And that can be done by letting us know, and we'll set it up as a breakout room after Jake presents. And I can think of already of two different instances or two different cases that worked really well this morning. And one of them was basically discussion about the tool known as TopCat, which is something that Jeff has presented or discussed at some length. And another one was further description of the DP 0.3 in the case if you wanted to learn more about the solar system science tools. So this is just a short announcement, but I think at this point I'm going to hand it over to Jake, unless there is anybody who has any more questions. I think I see no more questions in chat, and I believe there is nothing in the Session B Mondays Slack channel. Okay, so take it away, Jake.
Awesome, thank you. Hello, everyone. I'm Jake Kurlander. I'm a second-year graduate student at the University of Washington, and I helped produce the DP 0.3, the data preview 0.3 simulations, along with Pedro Bernardinelli and Joachim Moines, Sam Cornwall, and several others. I'm going to be leading everyone through a notebook I wrote, demonstrating the contents and some simple uses of each of the tables in DP 0.3. So first, we're going to get anyone who would like to follow along set up with that notebook using Git. So we're going to go through this. For anyone who would like to follow along, you should get to the Rubin Science platform, data.lsstr cloud, and see either this screen or a terminal session if you've already been following along in a terminal. And from here, we're going to clone the Git repository with a notebook. The Git repository is linked both in the email, the reminder of logistics email down here at this DP 0.3 delegated contributed notebooks link, or also if this is more convenient for you, in the slides on slide 8, we've got this second link here, same link. So if you'd like to follow along, head over to this GitHub repo, and in the code section, this bright button, go over and click on HTTPS and copy this repo link. And then once you've got that, we'll head back over to our terminal in the Rubin Science platform, and we're going to run git clone, and then the link that we just copied. And that's going to generate for us, perfect, a new folder called delegate contributions. And within that folder, we're going to go to ephemerides investigation, the second directory. And then we're going to go to DP 0.3 tutorial investigation. So not the one that says breakout. That one has the code contributed from the breakout session in the earlier version of the talk. All right. So hopefully anyone who is following along is now here. Anyone? Could not create worktree directory delegate contributions. Permission denied. Greg, could you cover that in the chat? I don't think I know what.
I think it has to do with the fact that it has to be a separate subdirectory that was created. I think that Jeff had.
Are they in the? You might be in the read-only directory, so you might you're gonna need to leave the notebooks. So if you, before doing that, do cd and then a tilde, that'll bring you back to your home directory where you have write permissions.
I think that's exactly what it was last time.
Okay, perfect. So cd tilde, and then the git clone again, and then move into ephemerides investigation and the DP 0.3 tutorial investigation, not the breakout one. All right, so we now have our notebook open. In this notebook, we are going to use the solar system tab to investigate the DP 0.3 tables, the simulated solar system dataset tables. So just like before, we're going to use get tap service, but this time instead of just calling it on the string tap, we're going to call it on the string SSO tap, or solar system object tap. And in general, everything that we're going to see that has to do with the Rubin Science solar system pipelines is going to start with those two letters, SS, for solar system. And we can query this tap and just ask it for the name of every table. So this is just a simple ADQL query. We're just asking for the metadata from the tap schema about the tables. We're just going to print out the name of each table. And so we see several metadata tables at the end, but then up top we've got these 8 tables split into 2 groups of 4. We've got all of these DP 0.3 10-year tables and another 4 identical 1-year tables. So DP 0.3 consists of 2 data sets, one simulating the full 10 years of Rubin, every detection of a solar system object by LSST in the whole 10 years, and the other is just the data from the first year and all of the science pipeline products from that first year. We can see that the 4 tables in question are dia source, MPC orb, SS object, and SS source. So these 4 tables are, and I see there's more chat. Okay, perfect work. Okay. So these 4 tables share between them all of the relevant solar system information that Rubin will collect. So for the real survey, in 11 years, when it's all done, all of the solar system information is going to be split between these 4 tables. And these 4 tables are broken down in terms of two divisions. So first is the division between object data and detection data. So two of the tables, SS object and MPC orb, describe the solar system objects that Rubin has observed. So the asteroids, their orbits, everything about a solar system object is in SSO object or MPC orb. The other two tables describe the detections. So each detection, each source, each spot of light in an image, all of the data about those is in SS source and in dia source. The other division is between information that the Rubin solar system pipelines generate. So quantities that are computed by Rubin solar system pipelines. Those are in SS object and SS source, while data that Rubin solar system pipelines inherit from upstream sources is in the other two tables, is an MPC orb and dia source. And in particular, MPC orb, that's the Minor Planet Center's orbit catalog. That is the list of all solar system objects known by the Minor Planet Center, the international IAU's clearinghouse for solar system objects. While dia source, that's the difference image analysis source, is generated by Rubin's difference imaging pipelines that are identifying transient sources across all Rubin images. And so the tables are broken down sort of by how this data gets made rather than by what the data is about or what the data tells us. And so it's really important to understand this distinction to be able to find the data we're looking for, because it's not always intuitive otherwise. So now we're going to just loop through the four names of these tables, and for each of them, we are going to service.search. So we're querying the SSO tap for just a single row from that table, and then we're just going to print out the columns of that table. So for each table, we're just going to print out its columns. And so here are the columns of each of the four tables. The Minor Planet Center orbits table, it includes all of the orbital information about objects. So we've got little e for eccentricity, inclination, longitude of the ascending known, argument to pericenter, and perihelion distance. These are the classical orbital parameters of an object. You also have things like the object's name, its full designation, and Minor Planet Center designation. The uncertainty parameter, this is how well constrained the object's orbit is. But there's also some information that isn't as relevant to anyone who isn't at the Minor Planet Center. So like computer, that's the name of the person at the Minor Planet Center who computed the orbit. So MPC orb, that's a Minor Planet Center database that we're just inheriting. And it has a lot of useful stuff and a lot of quirky stuff. Then SS object is the per object table that contains all of Rubin's information about this object. And so it has a whole bunch of information about Rubin bands, about Rubin colors. So we see all of these columns beginning with the letter G. This is the G band relevant data. So the object's absolute magnitude in G, its phase slope in G, and then covariance between its absolute magnitude and its phase slope in G band, the number of detections in the G band, the error on the absolute magnitude in G band. And so we've got a whole bunch of things for G band, and then those are repeated also for I band, R band, U band, Y band, and Z band. So the vast majority of the columns in SS object are about the colors of these objects and their per band photometric properties. But we also have things like the extendedness of the source, so how large that source is compared to a point source, that object's minimum orbital intersection distance, so how close it gets to Earth, and when Rubin discovered it, and when Rubin's first observation of it was. Then in dia source, this is the difference image analysis source that we inherit from upstream in the Rubin pipelines. So this contains all of the information about a source, about a detection and an exposure,
that might be a solar system object or might be anything else. So nothing in this, well, very little in this table is solar system object specific because this is inherited. So we have things like the band in which this object was, or in which this the band of the exposure that this detection comes from, the CCD visit ID, so just an ID for the exposure, the right ascension and declination of this source, the magnitude of this source and the error on that magnitude, the time of this source. So a whole bunch of sort of solar system object independent things. This could be a galaxy that has all these things. It could be a star that has all these things. Diasource doesn't know that it's talking about solar system objects here. And then finally, solar system source. So these are all of the computed things about these sources that must be solar system objects. So we have things like the heliocentric distance of this object and its state vector, its velocity, and position. We also have the phase angle and the magnitudes that we expected this object to be based on its orbital and photometric fit before this exposure was taken, and then distance and position from Earth, and yeah, other solar system object specific things. You can find even more information about these tables and their columns in the DP0.3 schema browser, which is linked here. We've got data types, units, and a description for every single row and every table. It's important to note that while this is the exact schema for DP0.3, and these 4 tables are exactly the 4 tables that will be available at the end of the survey and in the data releases, some of these column names might change, and there might be some changes to what columns are available based on how the development of the solar system processing pipelines goes over the next year or two. And there's further documentation at tp0-3.lsst.io. This includes, very importantly, a list of known issues. We found a few bugs with the simulation since generating it. The most important of these is a sort of 0.2 magnitude issue across the board. So pretty much every source is uniformly 0.2 of a magnitude too dim. And so this underestimates the catalog size by 30-ish%. So it's a pretty major thing. Things are too dim, but other than that, it's good to read the documentation. If you see something that looks wrong, check the documentation. It might be there. All right, so that's been an overview of the 4 tables and their contents and how to get some intuition about what table contains the information that you care about. We're going to move on to running some example queries in each table. But before that, I'd just like to pause and ask if anyone has any questions about what sort of data to expect in what tables, or about the tables themselves. Feel free to unmute or put something in the chat. All right, I'm not hearing any questions. So let's continue and start making some example queries of the solar system data sets. So in general, we're going to use the 1-year catalogs here just because they're a tenth the size in general. And so the queries run a little faster. First, we're going to query the SSO tap with this ADQL query. We're going to ask for the designation, so the name, the pericenter distance, so the object's closest approach to the sun, the closest distance it comes to the sun, and its eccentricity and inclination. So these are just the sort of 3 most important orbital parameters from MPCORB, so from the orbits catalog. And we're going to ask for these in order of pericenter distance and just limit the responses to 5. So this first query is going to give us the 5 objects in the DP0.3 catalog which come closest to the sun. And the second one, it's the same query, but it has descending here. So it's going to give us the 5 objects that stay farthest from the sun in the DP0.3 catalogs. So if we run this, it executes in just under half a second. And we have the 5 closest and the 5 farthest objects from the sun in the DP0.3 simulation. So right away, we see that the designations of the close objects all are very similar, and the designations of the farthest objects also share a format. And so these closest objects to the sun, these are all synthetic objects, synthetic objects from the Pan-STARRS S3M catalog. So one of the best synthetic models of the solar system is the Pan-STARRS S3M model. It was one of the precursor data sets for DP 0.3, one of the synthetic populations that we ran, and it comprises our near-Earth object population. You'll notice that these near-Earth objects, they come incredibly close to the sun. These are actually well within a solar radius, and so these very closest of the S3M near-Earth objects collide with the sun. So they're not very physical orbits. We're not expecting Rubin to find any objects that collide with the sun, because those objects shouldn't. They should have already collided with the sun, but that's just a little quirk of the data set. It's only an issue at the very close entail, but we can see that the vast majority of our near-Earth objects and the simulated ones are S3M objects. At the distant end, all of these objects, their designations follow the Minor Planet Center asteroid naming conventions. This is the year of the data when it was discovered, and then 2 letters that show the half month and the number within that year, or within that half month that this object was discovered. And so all 5 of these most distant objects, these are real known asteroids that we simulated as part of DP 0.3. And so we see that on the very interior end, all of our objects are simulated. The very exterior end, all of the objects are synthetic. So perhaps we should have used a trans-Neptunian object model, a distant solar system model that had more objects further out. But that's an overview of the populations. Most of the synthetic objects in DP 0.3 are either S3M, so this Pan-STARRS synthetic model, or real minor planet center objects. There's a couple of other populations we included. So there's also a Centaur model, and those objects have names beginning with CEN. There's a long period comet population, which have names beginning with LPC, and an interstellar object model, names beginning with ISO. And so we have a nice diverse set of objects spanning every orbital class here in DP 0.3, most of which are normalized, and got a real big population of objects to play with. The next table we're going to look at is SS source. This is the table containing information about individual detections of solar system objects, and in particular, containing information about the detections that has to be about solar system objects. So one lovely column in that table is phase angle. So this is the angle from the object's perspective between the sun and the Earth at the time of detection. So a phase angle of 0 means that we are looking at this object at opposition. It's directly away from the sun. Phase angle of 180 means that we are looking at this object directly toward the sun. So it's right between the sun and us. And so let's just find the detections with the highest phase angles. So again, this is pretty much the same ADQL query. We've just changed out the column names. We're just selecting phase angle from the SS source. We're ordering it by phase angle, descending, so highest first, and only taking the first 5 responses. Now, the source tables, they have a whole bunch more rows than the object tables, and so this query is going to take a whole lot longer. That took 9 seconds instead of half a second, but it quickly returns, and we find that Rubin is going to take several, not a huge number, but several detections of objects at very, very high phase angles. So these are detections of objects that are well interior to the Earth at the time of exposure. And so these detections are all from the twilight survey. So Rubin's going to spend a small fraction of its time at twilight, looking down toward the horizon and trying to find asteroids that are very, very close to the sun, even interior to the Earth. And if those objects are there, it'll be successful. It's got great great limiting magnitude, even pointing quite close to the sun. Moving on to SS object. This is the per object table out of the LSST solar system pipelines. And so, as we mentioned before, most of the columns in this table are dependent on bands. This is a pretty color-heavy table. And so what we're going to select from this table is the red band's number of detections and the red band's absolute magnitude. So we're going to order this by the number of red detections. So we're going to get the number of detections and absolute magnitude in the red band of the 5 objects that are observed most in the red band in the first year of the survey. And again, oh, that was actually way faster, less than a second. Okay. Yes, because this is per object table. Yeah, so less than a second, super fast. We find something pretty extreme. So LSST is going to uniformly cover most of the sky over 10 years and reach something like 830, 850 coverings of the sky over those 10 years across its 6 photometric bands. So sort of naively, we would expect that the most in a year, you're only going to get about 80 detections of an object. In any given band, you should only expect to get, 16, 15 detections of an object per year. But we're finding that there are some objects which receive in just one band, in just 1 year, it's the 1 year table, almost 150 detections. So 10 times more than we were expecting. And this is because of the deep drilling fields. So Rubin's going to spend a small fraction of its time surveying the same small survey area, just a few tens or maybe a few hundreds of square degrees, far more often and more deeply than the main survey area. And so there are solar system objects, there are asteroids and comets that are going to fall in those deep drilling fields and end up observed many more times than most objects. And so in the whole 10-year survey, there's a TNO, a trans-Neptunian object that moves so slowly and it stays in a deep drilling field over the entire course of the 10-year survey, and it ends up with 12,000 detections over the 10 years. So if you are interested in light curves and variability of solar system objects, there are going to be some objects with just incredible data sets out of this. Really huge numbers of detections. And we can see that the absolute magnitudes of these highly detected objects, they're very different from each other. So you don't have to be particularly bright or particularly large of an object to get a huge number of detections. You just have to fall in the deep drilling field and stay there for a long time. All right, the last of the 4 tables is the difference image analysis source table. So this contains every detection of every solar system object over the course of the survey, but only the information about these objects that is not solar system object specific. So only the things that the difference image pipeline would have already produced, like right ascension, declination, and magnitude. Now, the table on its own is really big. Let's see how big it is by selecting count of everything from DP03 catalogs 1year.diosource. So the 1-year diosource catalog contains 48.3 million sources, and it would take a really long time not that long. The tap is very fast, but sometimes you might not need all 48 million. You just want a statistically significant sample of the whole table. And so it would be nice if we could take a random cut, a uniform random cut of the table, and operate on that. Maybe we only need 100,000 to get the precision that we need when we want to learn something about this table. So for example, what I'd like to do is plot just a histogram of all of the detections by magnitude. And I'd like to do that splitting up by band. So we can see the contribution of each photometric band to the Rubin solar system science, just the whole data set of solar system objects. But we don't want all 48 million, that'll take a while. So we need to make this random uniform cut, take a uniform slice out of the table. And it turns out there's a really easy way to do this because the Rubin IDs, so there's two IDs in the tables. One of them is SS object ID. This is a 64-bit integer that represents the solar system object that generated the source. The second ID is dia source ID. This is only for the sources. This isn't per object, but all four tables have SS object ID, and it's a 64-bit integer it's produced by a hash function. And so hash functions are effectively random. They effectively are equally likely to choose any of the 2 to the 64 integers. And so we can treat this as a random sample. So let's say that we want, here I've just written a 1/4% is the fraction of the table that we want. We can grab a 1/4% of the table by taking a number that's almost 2 to the 63. So we take 2 to the 63 times 1 minus that fraction. We double it because it's 2 to the 64, and there's positive and negatives. And we're going to select band and magnitude from DP 0.3 catalogs where the dia source is greater than this fraction, this number that's almost 2 to the 63. And so this is going to give us a uniform slice by treating dia source as a random sample. And we find that this ends up running a whole lot faster than it would to query the entire table. We get 120,000 results back, and if we just divide that by 1/4%, we get 48 million.3, which is what we the whole size of the table. So perfect, it worked. And now we can plot 1/4% of the table very quickly without having to hold the entire table in memory. Here we've just taken a nice even sample from across the table. And it's important to do that instead of limit, because if you just add like limit 120,000 to the end of this, the table's sorted in some order already, so it won't be a fair draw. Okay, and so from this plot, we see that the I band and the R band are the biggest contributors to the Rubin solar system yield. So they each have at least 2, maybe 3 times as many detections as the G and the Z bands. And then the Y band is really not doing a lot here. For solar system science, the R and the I and the G, and then also the Z bands are the really important ones, the ones that are really driving our solar system discovery. Okay, let's see. The next thing we're going to talk about is SS object ID. So this key that pulls all the tables together. It's one column that's present in every table. We can use it to do joins. I should just ask, I did not actually set a timer for myself on this talk. Greg, how long do I have?
I remember your previous presentation, so I think you're doing fine. It's
okay.
I think you have another 5 to 7 minutes or something.
5 to 7 minutes. Perfect. Thank you. All right, so let's move on to SS object ID. This is the index. It's a 64-bit integer which encodes the solar system object that a row is referring to. So in the per object tables, SS object and MPC orb, each row has its own unique SS object ID. In the source catalogs, you're going to have one row with that SS object ID per detection or per source. So you might have a whole bunch of rows with the same SS object ID. But we can use this to join together the different tables and bring together information from the different tables, since the information we care about is often spread out across these tables. So to practice with this, we're going to investigate 3 famous objects. So we've got Bennu, which is a near-Earth object. This is a pretty large not threatening, but visited by some robotic missions. Asteroid, I think there's been a sample return. I think there's been a sample return. I don't trust me on that. We've got Hallman, which is an asteroid named after the chair of the users committee for this for LSST. And then Eris, which is a very, very large dwarf planet out in the far outer solar system. So to start, we're just going to grab the Minor Planet Center orbits catalogs information about these three objects. So MPC designation is the Minor Planet Center name column, and we know these objects, we know their names, and we want to learn about them in the Rubin platform. So we're going to query on these names, and then from that table, this is we've got 3 rows, one for each object. So we found all 3. We're going to grab the SS object IDs. So this is the Rubin key, the Rubin name of each of these objects. We're just going to print those out. So here we have our 4 integers, or excuse me, our three integers. These are the Rubin names of these objects, and that's how we're going to query them in the other tables. And then let's select all of the DIA sources, so all of the difference image sources, which have SS object IDs in this set. And so that is actually super fast. It takes just half a second to grab all of the detections of those 3 objects from the 1-year from the 10-year catalog. We've moved up. Okay, so we've got 10 years of data for each of these 3 objects. And then we're gonna group these by the name listed in DiaSource. So DP0.3 contains some columns which are not going to exist in Rubin. It contains several truth columns. So these are columns which contain information that we as the people making the simulation knew, like what object created what source. This is a column that you should not expect to exist in the real Rubin data because it's there won't be truth information in the real data. But we group it by that and just print out these names again. Okay, so we've got the object spec that we were hoping for now in DiaSource. And then for each one of these groups, so we've got the object ID and the set of detections associated with this object. We're going to make a few plots. So our first plot is going to be right ascension versus time. So the modified Julian date, the times of these exposures versus the right ascension. The second plot is going to be the declination over time. Same thing, the second coordinate. And the third plot is going to be the sky path. So right ascension versus declination. And we can see each of these objects, their paths as charted out by Rubin over the 10-year survey. This is the main belt object. We can see that it has sort of this one large orbit as the 10-year survey progresses. It's one big sine wave pattern, but it progresses all the way around the orbit from 0 to 360 in right ascension, but it stays pretty constrained in declination to the ecliptic because it's a nice, well-behaved main belt object. Then we've got the near Earth object. It's got a sort of much more sporadic path, a lot more chaotic looking on the sky, and it travels much higher in declination, or much lower, down to -40. Finally, we've got the trans-Neptunian object, Eris. This one, almost all of its motion here that we see over the 10 years is due to the Earth's motion. So this annually repeating pattern is much more pronounced than its actual motion through space. But it's just because it's very, very far away and very slow moving, and we're moving at the same speed no matter what. So we've got this information, these right ascensions and declinations, sky path, out of this table using SS object ID. If there were information in SS source, so perhaps we care about the XYZ positions at each of these detections or the phase angles, we could query that the same way and then join those tables together. And that's really where the power of DP 0.3 and really where the power of all of these big tables of Rubin itself lies. It's going to be very important to understand what what data you need for your science, and then be able to query it quickly from Rubin Science platform or from Rubin. And so working with these tables is going to be a big part of making science quick and easy once we have real data. There's a bit more that I'll work on in the breakout session with anyone who's interested in joining. We're going to learn how to use JPL's horizons. So this is this is JPL's orbit catalog and ephemerity service. We're going to compare DP 0.3 to horizons and see how accurately we've simulated these orbits. But I'll just do that in the breakout room. So thanks everyone for watching, and that's my talk.
Thank you very much, Jake, for a wonderful presentation. Very clear as always. So let's wait for people to put their questions into either chat or into the Slack channel. I don't see anything in the chat, so let me just verify that there's nothing in the Slack channel, and I think that that's probably right. Yeah. Okay, so at this point, we're going to take a short break. Everybody needs at some point to get their coffee or maybe go to the restroom or something like this. We'll meet up here maybe at maybe in about 5 minutes. Say let's make it about 8:37. And then what we're going to do is we would go into the breakout rooms, and let me just show you what are the breakout rooms that would be useful to cover. Let me just go back to, so now I can go back and start sharing my screen. Okay, and I have few suggestions here. I know there was one suggestion from somebody to do a bit of exploration of light curves, and I can do it from the Rubin Science Platforms portal. Again, Jake already mentioned that he might be able to go to have more discussions of the solar system simulation tools. And if any of you are interested in doing any kind of top cut type study, Douglas, I know, has done that in the morning session, and that worked out really well. And then if there's any more questions about the Rubin Science Platform notebooks in general, maybe Jeff can cover this. This is just a suggestion. Are there any other suggestions from maybe the organizers or maybe any of the attendees that would like to have covered in the breakout session? All right, so if this looks good, I'm gonna just continue and make those breakout sessions. But in the meantime, I'm going to stop recording because I think the breakout sessions generally are not recorded. So let me do this. Okay.